I'm very happy to be here in the fourth version of the 24 Hours of Concrete Knowledge. My name is Juan Francisco Correal. I am a full professor of Universidad de los Andes in Bogota, Colombia. I'm here to present the study of intermediate structural wall based on Colombian cyclic code. I want to start this presentation with the research significance. And I want to start with a question: why we need intermediate reinforced structural walls? The answer to that question is because half of the population in Colombia lives in intermediate and seismic hazard zone, as you see in the map of the left, which is in the yellow zones. Here in the right, there is some cities that are located in that regions. And actually, the two main cities, which is Bogota and Medellin, where we have 20% of the population is located in that zones. We can design or use the special reinforced concrete specifications in order to design this kind of system in intermediate seismic hazard zone. But based on a study did by Professor Luis Enrique Garcia in 1995, it will increase the cost of the building of close to 20%. In addition to that, and based on the national statistic, this kind of system of walls has been used very often and good in Colombia. Actually, based on the statistics of the last year, 2023, 50% of the residential buildings has been built with this kind of system. We have our Colombian code that has specifications for this kind of intermediate structural walls, and it's probably the only design code in the world that has this kind of specifications. And we have been using these specifications for the last probably 20 years. The ACI 318 actually has only specification for intermediate precast walls. To date, there has not been a significant earthquake or of an intermediate hazard zone in Colombia, and the specifications for the intermediate reinforced structural walls based on the Colombian code has not been verified or tested. No research has been conducted for intermediate walls either. Therefore, we decided to do a research project that the objective was to evaluate the seismic performance of intermediate concrete structural walls. In order to do that, Universidad de los Andes joined effort with an association that has all the main construction companies. And also we did an agreement with a very important structural company in Colombia, P&D, that was in charge of the design of all the archetype buildings that I'm going to show you later. The whole project took us like 3 years that implied full-scale testing of walls and the application of FEMA P695. Why we use FEMA P695 is the question. Because the methodology that the FEMA P695 has provides a rational basis for determining building system performance factors. If we apply this in a good manner, it will be resulting in equivalent safety against collapse in an earthquake that is comparable to inherent safety against collapse intended by the current seismic codes. And this methodology allows to use different seismic force resistance system like something that we have in Colombia as the intermediate reinforced concrete walls. The methodology has 6 steps that I'm going to show you through the presentation applied to our study. The first step is to define the system. Of course, the system is already defined by the Colombian code, and the Colombian code that has intermediate structural walls specifications were based on the special structural walls of the ACI 318 of 2008. But there are some modifications, especially in the boundary elements. One of the first, the first modification was related with the compression zone that should be reinforced with boundary elements. When C, the equation C is higher than the equation that you see there. And that equation has a ratio that should not be taken less than 0.007. So in order to comply with the intermediate seismic hazard zone, we lower the ratio to 0.035. The second change that we have in our Colombian code was related with the compressive stress limit. The specifications said that you have to you have to use or have to have a special boundary elements when the compression stress limit exceeds 0.2 f prime sub c. Also, the specifications tell you when you can discontinue the special boundary elements, and is when you have a compression stress less than 0.15 f prime sub c. In order to comply with the intermediate high-speed hazard zone, we increase that stresses to 0.3 f prime sub c at 0.22 f prime sub c. The third change was related with the transverse reinforcements for boundary elements that should satisfy spacings for intermediate columns instead of special columns that are mentioned in ACI 218. And we have a spacing limit that need not be taken less than 100 millimeters. Here I'm just show you the spacing that comes from intermediate columns that should not be exceed the smallest of A through O D, as you see in the screen. In addition to that, we review the reinforced concrete walls performance worldwide, mainly the behavior of this kind of system in Chile earthquake in 2010 and in New Zealand earthquake in 2011. Also, we did a compilation of 26 experimental wall tests, mainly to the review of different papers and proceedings, like this one here by Professor John Wallace and Jack Melly. Also, we built a database with 39 residential buildings in Colombia, and we took all of these buildings and review most important common types of walls, like you see here, the plan view of 2 different buildings. When you see different configuration walls, like L-shaped walls, I-shaped walls, rectangular or linear walls, and also depends on the height of the building, and you also end up with having boundary elements. Then we go to step number 3 of the methodology, that was the archetype development. In order to do that, we have in total 12 archetype types that are grouped in 4 groups. All are structural systems by intermediate structural walls. The gravity load was defined as a low because it varies between 3% and 6% of the wall axial strength. And the intermediate level of seismic hazard was divided in 2 levels, in minimum and maximum. The minimum, once we have these lows defined, we can design 3 archetypes for the first group, which was that there were 5-story, 6, and 8-story buildings. And then we increased to intermediate maximum level of seismic hazard. And then we use exactly the same buildings in height with the same stories 5, 6, and 8 than the group number 1, but with a higher seismic hazard. Then for the group number 3 and 4 is similar to 1 and 8, but we have buildings of 12, 16, and 8-story in each group. In total, 12 archetypes. Just to show you here the design spectrum for the intermediate maximum level, which is the red spectrum, and then here the green, which corresponds to the intermediate minimum level of hazard. And just to show some comparison with the ISE 7, with the C, that is like kind of intermediate seismic hazard zone in US, you see that there is in the same range that in Colombia. Also, I show you here like the intermediate mid-level, which is used to design buildings in Bogota and Medellin, which are the 2 main cities in Colombia. The step number 4 was to develop the computer program. We use computer model. We use an OpenSys computer program that we use the force-based element and fiber section with nonlinear materials. We use a material regularization recommendations by Pugs, Lowe's, and Lingman. And we also use a confined concrete models for confined elements like boundary elements by Satogli and Rusby. In order to calibrate our computer model, we decide to do different test setups or different tests of walls at full scale. We use the setup of two-story wall, as you see in the picture in the left, with stories in height of 2.4 meters each. And we test 5 full-scale reinforced walls based on the archetypes buildings that I just showed you. The first two were two L-shaped walls with 8 centimeter thick, one reinforced with well wire and the other with deformed boards. But exactly the same, but they changed only the reinforcement. Here are the pictures of the two L-shaped walls with 8 centimeters. The third one was an I-shaped wall with 15 centimeters thick, reinforced with deformed boards in the web and flanges. As you see, there is some extension of the web at the end of the wall. And this is because it's typically found in the architect buildings. The last two walls that were tested were two rectangular walls, one with a longitudinal ratio of 1% at the end of the walls, and the other with a boundary elements with a longitudinal reinforcement ratio of 2.3%. Just to explain you a little bit about the setup, the idea of the setup is that we want to simulate the real axial force, shear, and moment that is going to have that we're going to have in a wall for different height. So in that way, we use this setup with two vertical actuators and one horizontal. So this is a video that I show you here. This is the actual load that depends on the height of the building. Then these two vertical actuators stand the arms is give you part of the moment that is going to go to the base, and the other part of the moment is the horizontal force times the height, and the shear comes from the horizontal actuator. In that way, we have the real forces in the bottom of the wall. And there is the results of the experimental results compared with the simulation, the computer simulation. As you see, there is a very good agreement, not only for L-shaped walls, but also for I-shaped walls, as well for the walls, rectangular walls with boundary elements. Something that is very important for the model is that you need to be able, with the model, to predict the failure of the walls. This is very important for the model, and this is something that the methodology of the FEMA asked for. The 5 studies perform early analysis. In order to do that, we have some building model assumptions. One is that we use a model damping of 3% based on the ASE 41. We also use assumption of rigid diaphragm, and we calculate or include the torsion stiffness of the wall sections in the whole building. Once we have the model ready, we perform a pushover analysis in each direction, as you see here in the picture, and then we take the average of the ductility capacity in order to be data that we're going to use in the step number 6. Then we perform a nonlinear response history analysis with the 22 pair of predefined far field record that has the methodology implied. In other words, we perform an incremental dynamic analysis of 44 records because we have to apply 22 in each direction. In total, it give us around 440 analysis per archetype. After that, we're ready to determine the collapse margin ratio for each archetype model. So this is just a picture how we did that. The dots are the failure for each earthquake that we found, and then we have a distribution of the collapse intensities. Then we take the medium of the collapse intensities, and then we calculate the MC intensities that come from the design spectrum that we can use. And then if you take the median collapse intensity divided by MC intensities, it gives you the collapse margin ratio based on the methodology. And then it is possible to do some adjustment, depend if you use a 3D analysis. That was our case. And also it is needed to do some adjustment of the collapse margin ratio for the ductility as well. Then for the step number 6, which was the performance evaluation, it is important to determine, or is implied, or important, or is needed to determine the system collapse uncertainty, beta total. And this is based on this equation that has 4 different betas. The first beta is related with the dependent utility capacity. Then the last 3 betas are related with different things. The first thing is related in the table 5.3, which is in the FEMA, that is related with the quality rating index of the archetype models. So in that way, you have to qualify that. We qualify as a medium based on the accuracy and the representation of the collapse characteristic, which give us a beta that calls a fair beta close to 0.35. Then we do the same procedure, but now with the table 3.2, that is the uncertainty related with the experimental investigation. And in that case, we have high, for the confidence of the test, and medium for the completeness. So it gives us a beta of good. And the same we did with the design requirements, that we have beta of 0.35 based on the qualification of confidence and completeness of the design requirements. Once we have the beta, we can have the beta total and go to table 7-3 and then compute the acceptable value of adjusted collapse merging ratio for a collapse probability of 10% and 20%. The 20% that is here, this number here, is going to be used to compare with the margin ratio that we calculate from every archetype. And the 10% collapse as accepted by adjusted collapse ratio is going to be used for the average of each performance group. Here is a table that summarizes all the results. So I'm just going to explain you the first 3. The first 3, as you see, is the group number 1. And here are the ACM arc that we calculate from our nonlinear analysis. And this is that it comes from the tables that I show you. So as you see, as long this number is more than this one, it passed. So in all the groups, as you see, and here is the average just to compare the group. Okay, so as you see, in all the cases, it passed. So so this is the way that we prove that the intermediate structural walls specification in Colombia are compliant with this methodology, which is a safety issue that we are proving here. Also, we did a case study in Bogota and Medellin with 2 different buildings that has 6 stories each, but they are different. That one is reinforcement with weld wire and the other is with the former bars. As you see, when we have weld wire, the walls reinforcements with weld wire, they fail the FEMA P695. As a conclusions, that was based on the limitation of this study and are established for intermediate structural walls based on the Colombian seismic code, are the following. The first one is the selected archetypes designing for the minimum and maximum levels of Colombian intermediate seismic hazard zone, and with the design criteria based on the Colombian seismic code, meet the requirements of FEMA P695. As you see in the table, the archetype located in Bogota and designed for a medium level of intermediate seismic hazard zone and using the former bores meets the requirements of FEMA P695. Now, if we take exactly the same building but change the reinforcement of the walls by using weld wire, does not meet the requirements of FEMA P695. With that, I want to finalize my presentation. Thank you very much for your time. Here is my information if you have any question. Thank you very much.
Thank you again for a very interesting presentation. I don't see many questions. I don't know if Bernie sees additional questions.
Yeah, I have a couple questions here from.
Sure. Please go ahead.
From the ACI staff engineer. Notice that 6 inches, 150 millimeter thick walls with one curtain wall of steel reinforcement was tested in the lab. Does Columbia use 6-inch thick walls in practice in building seismic resistant multi-story buildings?
Hi, Bernie. Yeah, the question is, yeah, we kind of use, but this is the thinner walls that we can use. But in the building, the recommendation is that you not only use this kind of thin wall, you use in the building you have a thicker walls that are more responsible for the seismic loads. So, but yeah, we test this kind of walls because especially are used in intermediate seismic hazard zone in Colombia, and for let's say some stories like low stories buildings up to 6th floor at most.
So you're saying it's another product that you can use depending on the size of the project. Bigger buildings would require thicker walls, and the smaller buildings can use the 6-inch.
Correct.
Got it. Thank you. And yeah, it's good to see you again from Prosemco.
Good to see you. Yeah, good to see you.
I have another question here. It says, when designing multi-story concrete buildings with special concrete structural shear walls to resist seismic loads, what are the common or minimal wall thicknesses? I guess you just answered that, really.
Yeah, in the special, there is actually a requirement in 2018, 19. Currently, that is the minimum thickness is related with the boundary elements. No, not for, let's say, the boundary element has a minimum thickness, but if you don't require a boundary element, now the thickness is not too clear. Is something that actually the engineering has to figure out based on the loads and in the demand.
Okay. And I think I don't think there's any other questions that I can see. So
I don't see it.
So thank you, Juan Francisco. Always good to see you, and thanks for sharing your knowledge. And Gonzalo, you want to introduce the next speaker?
Sure thing, Bernie. Thank you again. Our next speaker is a very young engineer from Universidad Nacional de Colombia. He graduated as an engineer there, Kevin Andrés Tambi Torres. And now then he studied in the Escuela Colombiana de Ingeniería Julio Garavito, where he got his master's degree. And he currently works there as a full-time professor since 2022. He's the co-director of the Structures, Materials, Constructions undergraduate investigation group at the university. And he works currently looking into sustainability with various additions in concrete. For today's talk, he will be talking about the shear behavior of post-installed anchor connections strengthened with FRP laminations. So again, thank you again for the participation, and let's see what Kevin has to tell us about.
Hello everyone, my name is Kevin Tammy. I'm very happy to participate in the 24 Hours of Concrete Knowledge by ACI. I am a full-time professor at the Escuela Colombiana de Ingeniería, and today I will present you a study regarding the shear behavior of post-installed anchor connections strengthened with FRP laminates. This presentation summarizes some of the results obtained in my master's graduate work, whose advisor and co-advisor were Mr. Gustavo Tumialan and Ms. Nancy Torres. So, what was the problem we wanted to address? Well, post-installed anchor connections have a wide range of structural and non-structural applications. Wherever you look, you may find something anchored to concrete. Now, these anchors may be subjected to different types of loading. However, we wanted to address those affected by shear loading. Some examples may include steel bracing connections to concrete frames, as well as the anchoring of facades and railings in balconies. Now, it may be somewhat intuitive, but the capacity of shear-loaded anchors is highly dependent on the distance between the anchoring system and the edge of the concrete member. Typically, failure occurs when the shear load generates such a displacement of the anchor that it induces a tensile stress within the concrete that exceeds its capacity. leading to cracking and the subsequent formation of a breakout cone. This failure mode is known as concrete breakout. However, concrete breakout can be controlled. If the use of anchors is planned since the design stages, a casting anchor reinforcement may be employed. This reinforcement typically corresponds to steel hairpins, which take the tensile stresses of the concrete, preventing the total formation of the breakout body. Of course, the main advantage of hairpins is an aesthetic one. However, to use them implies that every single connection subjected to shear has to be considered and detailed since design, and that is very uncommon. So, what do we do if we have post-installed anchoring systems? Well, some alternatives may include the reconstruction of the concrete elements or the strengthening of the connection. On the strengthening side, the use of FRP emerged as a possible alternative. But what are the advantages of FRP? Well, first, it generates no affectation on the internal concrete structure, and second, it may be adjusted to the geometry of the existing structure, which is very important. So the idea of this study was to use FRP laminates as if they were some kind of post-installed anchor reinforcement, acting as some sort of external hairpin. These were some of the objectives of the investigation. We wanted to assess the behavior of the reinforced specimens and compare parameters such as maximum load, unit strain, and failure mode. It was also of great interest to compare different geometric configurations of the reinforcement to analyze their failure mechanism. And finally, as this study evaluated a post-installed anchor reinforcement, it was also important to compare the obtained results to those of specimens with casting anchor reinforcement, this is, with hairpins. Now, everything related to anchor design was done according to the guidelines in ACI 318, and everything that involved FRP considered ACI 440. Now, these are the three failure modes of shear-loaded anchors as represented in ACI 318. Concrete breakout on the right is the most common when anchors are close to the edge, as I mentioned before. On the center, we have concrete pry-out. This one occurs farther from any edge, and it happens due to the eccentricity of the shear load in relation to the geometric center of the anchor, which generates a moment and a basculation movement of the anchor. This failure mechanism also induces tensile stresses, but at the back of the anchor. Finally, on the left, we have steel rupture, which depends entirely on the geometric and material properties of the anchor being the ultimate controlling limit state. These are the material and geometric properties of most of the elements used in this study. We used concrete slabs with a compressive strength of 21 megapascals. The anchors were number 5 ASTM A193 grade B7 threaded rods. Hairpins were constituted by a normal grade 60 bent rebar, and lastly, these were the properties of the CFRP laminates. Considering the previous parameters, this graph summarizes the behavior of a single anchor relating its ultimate shear capacity to its distance to the edge of the concrete member. As you can see, as we increase the distance, the capacity also rises. However, from one point onward, the capacity does not depend anymore on edge distance, but solely on the anchor's material properties. So the red zone corresponds to a concrete breakout controlled failure, and in the green zone, steel rupture prevails. For this project, specimens were tested at edge distances of 50 and 100 millimeters, as both are common values in real applications, and because concrete breakout would be their controlling failure mode. However, the results I will show you later focus mainly on the 100 millimeters specimens. Also, given the aim of this study, we wanted to formulate a reinforcement scheme that would always lead to steel rupture, so the connection did not depend on edge distance anymore. The next step consisted in designing the anchor reinforcement. First, it is important to notice that although the type of load is shear, the reinforcement would actually be subjected to tension, as its main function is to take the tensile stresses that generate cracking in the concrete. It is the same principle as for stirrups in concrete beams or concrete columns. As steel rupture occurs theoretically at a load of 75.5 kN, this was the force for which the reinforcements were designed. However, due to the different configurations, it was necessary to elaborate some strut and tie models to know the tensile force that would be acting on each element. Finally, equating the acting force to the capacity of the reinforcement, it was possible to obtain for the CFRP the required laminate width, and for the hairpins the required rebar area. Regarding CFRP reinforcement, its capacity due to tensile loads is as follows, which results in a total required width of 12.6 inches or 320 millimeters. However, a decision was taken to reduce this width to just 10 inches or 254 millimeters to assess if it was possible to obtain the desired results with a smaller area of reinforcement. Also, important to note that no reduction factors were employed. Given the required width of 10 inches, various reinforcement configurations were elaborated, varying the number of laminates that would sum up to the total width required. In addition, some specimens were constructed with just half of the required width of reinforcement, which would be 5 inches. Regarding notation, the R refers to a reinforced specimen followed by a number, which signifies the number of CFRP laminates placed on each side of the anchor, and followed by another number, which defines the width of each laminate in inches. In this slide, it is easier to assimilate the different FRP configurations. The X configuration is important, as in this scheme the laminates are oriented so their axis is perpendicular to the concrete breakout crack path, which would theoretically lead to a better performance of the reinforcement. That is all regarding CFRP design. On the other hand, the hairpin design was similar to that of a steel member in tension. To obtain anchor rupture, a steel hairpin with two legs would require an area of 90 square millimeters. Therefore, number 4 bent rebar was employed. Likewise, for the hairpin design, no reduction factors were used. This is the scheme that shows the hairpin and its location within the concrete member. As you will see later, the performance of this type of reinforcement is highly dependent on the quality of its installation. After the testing and processing of the data, these are the results. Here we have the experimental maximum shear load, the relation between the experimental and the theoretical failure loads, and the relation between the capacity of the reinforced specimens and the experimental failure load of the unreinforced specimens. Finally, last column contains the observed failure mode. You may see that experimentally controlled specimens failed at a higher load than what is expected according to theory. Recalling that no reduction factors were used, this evidences that ACI 318 equations are conservative in regard to concrete breakout. In the case of hairpin reinforced specimens, two failure modes were observed, what we could name a pure anchor rupture and an anchor rupture preceded by concrete breakout. the systems that evidenced the latter failure mode did not manage to achieve a strength similar to that of anchor rupture. This shows uncertainty in the response of casting anchor reinforcement, as the cause of this variability is attributed mainly to minor differences in the installation, even if great attention was paid to this process, ensuring contact between the anchor and the hairpin and guaranteeing minimum concrete cover. Additionally, specimens with total width of reinforcement concentrated in one strip on each side evidenced steel rupture every time, developing an increasing strength of 2.21 times that of unreinforced specimens. Also, specimens with total width of reinforcement but distributed in two FRP sheets on each side of the anchor showed a variable behavior, as one of these specimens achieved steel rupture, but the other two evidenced concrete pry-out, which led to the bonding of the CFRP laminates. This shows us that concentrating the composite material near the anchor is more effective than distributing it. On the other hand, specimens with just half of the reinforcement always showed this last type of failure mechanism, a concrete pry-out that generated the bonding of FRP sheets. Their behavior in general was similar to that of the specimens with total area with two laminates on each side, implying that the outermost laminates did not receive a significant force. This idea is supported by their unit strain behavior and theoretically by their strut and tie model. Finally, specimens with half of the required area of reinforcement but arranged in X configuration achieved steel rupture every single time. This is very important. With just half of the total reinforcement, which we should remember that is less than the calculated required area, these specimens reached steel rupture. And this is due to the orientation of the fibers, which were perpendicular to the average experimental concrete breakout crack path. This graph summarizes the force versus displacement behavior of most specimens. The black curve represents the unreinforced control specimens. You can see that failure occurs at a higher load than the theoretical one of 22 kilonewton. Then we have reinforced specimens. Clearly, every reinforced specimen surpassed the control capacity, changing the failure mode and achieving a higher ductility as well. You can see the moment the reinforcement starts to work, which is after the initial cracking associated to concrete breakout, and this is evidenced in a change in the slope of the behavior, which is the green zone. Now here are some pictures. On the left you can see the breakout body of the control specimens. On the top right side we have the pure anchor rupture that I mentioned before on the hairpin specimens, and on the bottom right side we have the breakout then rupture failure mode, which was observed in all the other hairpin reinforced specimens. These are the total area concentrated in one laminate on each side specimens. You can see the shear rupture of the anchor and the formation of concrete breakout and concrete pry-out cracks, which did not propagate far from the anchor, as the tensile stresses were effectively taken by the CFRP. This is total area distributed in two laminates on each side. You can see that as the laminate width is smaller, concrete breakout cracks propagated beyond the innermost laminates. This ineffective crack control is what led to the formation of a concrete pry-out body, which caused the bonding of the FRP. This is a specimen with half of the total reinforcement. We have concrete pry-out here as well. You can notice that cracks originate at the back of the anchor. And finally, this is half the reinforcement in X configuration, As steel rupture was achieved, we can conclude that the direction of the laminate has a notable incidence in the overall capacity of the system. Regarding unit strain behavior, strain gauges placed close to the anchor showed higher unit strains on the FRP than those located far from the anchor and the concrete breakout cracks. Here it is possible to observe that distributing the reinforcement into various laminates is ineffective, as these laminates do not show a significant strain. These are the relations between the maximum unit strain obtained near the anchor and the ultimate design unit strain of the CFRP, all calculated in specimens that achieved steel rupture. All the relations are similar, showing that given the steel properties used, the anchor failure occurs when CFRP is stressed to about 36 to 38% of its maximum capacity. Lastly, an important note. The results I previously showed you corresponded to anchors located 100 millimeters from the border. However, for 50 millimeters anchors, some aspects of their behavior were similar and some of them were different. But what I wanted to tell you is that when the anchor is placed really close to the edge and the reinforcement consists of individual laminates on each side, then a concrete slice forms between the FRP sheets. This failure mode limits the capacity of the system, as steel rupture is not achieved. Better behavior is obtained if just one laminate is used, allowing the passage of the anchor through the fiber, as we see in the video. In this specimen, we obtained steel rupture. These are some of the conclusions of this study. The use of CFRP as a post-installed anchor reinforcement does increase the strength and the ductility and changes the failure mode of shear-loaded anchors. To reduce the behavior's variability and to increase the confinement of the concrete, it is recommended to use one single laminate instead of distributing the area of reinforcement on various individual strips. X-reinforced specimens work really well, but their effectiveness depends on how well the crack orientation is known. If it is possible to reliably predict the angle of the cracks, then X-reinforced specimens are optimal. Lastly, yes, the response of CFRP reinforced systems depends on the quality of their installation, as it should be done by certified technicians. But the results show that there is a higher uncertainty associated to hairpin reinforced specimens, as their response is highly dependent on their installation process. These were the sources consulted for this project, and here is my contact information if you have any questions. Thank you very much.
Thank you, Kevin, for a great presentation on fibers, and the results are very interesting regarding the distances and the results based on the code and what can actually happen with the fibers. I really don't see any questions, Bernie, but I don't know if you have some from the ACI group.
I have two. One is, can FRP strengthening wraps be successfully applied to existing concrete drilled pier foundations near the column anchors located directly below existing floor slabs to strengthen these piers? Does that make sense?
Sir, could you repeat it, please?
Sure. Can FRP strengthening wraps be successfully applied to existing concrete drilled pier foundations near the column anchors located directly below existing floor slabs to strengthen these piers?
Well, I think we all know that one of the main advantages of FRP is that it can be used in some aggressive environments, as it could be for piers. but as this study showed, I focused mainly on shear loaded anchors. So in this type of applications, maybe some tension would also be included. And actually, this project, the continuation of this project would actually address the influence, or maybe the influence of FRP sheets on anchors that would be subjected to other kinds of loads, to tension loads, or to the interaction or combination of tensile and shear loads. So at this moment, maybe I could not provide an exact response, but I think that it could be possible to use this kind of reinforcement on those applications, but we have to study them.
Yeah, you'll be doing more study on that in the future, and maybe you can
Yes,
report back to us on that then.
that's correct.
Great, thank you. And I have another question. Can the FRP wraps around anchors in concrete piers be placed in a reliable, consistent manner so that there is high confidence that the wrap will add concrete breakout strength capacity without any future delamination? Are they inspected over time?
Inspection is very, very, very important on FRP.
Yeah,
And I don't remember exactly the section of ACI 440 when it actually says, well, you have to do continuous revision of the state of the laminates, like every time. And you have to also guarantee that the loads that are acting on the member that is strengthened with FRP still has some capacity to support some part of the load as if it didn't have the FRP reinforcement. So
you're saying it's sort of a shared strengthening then, some from the existing and then some from the wrap.
yes, exactly.
Okay, got it.
And at the time, it's very important to always do maintenance and to review how is the state of the FRP.
Absolutely. I think, yeah, always to monitor the health of a building is, I think we've seen over time, it's critically important.
But it's actually very reliable to use FRP, as I showed in this study. It's, I would say, yeah, well, no, I cannot actually say that, but FRP does have a significant increase in the strength capacity of the anchors, and it behaved pretty well, and it controlled the cracks effectively. And there are some sort of things that you have to take into account, like the confinement that the FRP has to the concrete. That is very important to guarantee not so wide crack formation, but it's actually very reliable, a very reliable alternative of reinforcement.
Well, that's why your studies and research like this actually build more confidence in the system. So thank you for doing that.
No. I would like to continue with this investigation and to see what's up next.
Okay. So we have a little more time, Gonzalo.
I think there's some room for ACI or for sponsors to show and learn. Have like about 10 minutes. But yeah.
Well, I have one planned for the next hour. So are there any other questions? I saw there were 3 hands raised in the audience. I'm not sure what they are asking instead of 2 now. If they could write in what their questions are, that would be beneficial. Now let's check Q&A. There's another question in the Q&A, I think.
I think there is one for Kevin right now. I mean, that's the latest one. I'll read it for you.
Okay, go ahead.
It says, I would really love, it's from, it says, dear facilitator, I would really love to know how can I predict cracked angles to ensure the strategic placing of extreme force. This is Labor Charles Uganda. So I think they would be for Kevin when he was talking about the X placement of the fibers. So yes. Maybe Kevin can try to determine what's the best placement for this X type X configuration reinforcement.
All right. So ACI 318 in chapter 17, which is the part that corresponds to anchor design, it specifies, it's based on the CCD method, and it specifies, or it supposes, a crack angle of 35 degrees. However, what we found in this investigation with the control specimens was that the average orientation of the cracks was of around 17 degrees. So 17 degrees in relation to 35 degrees, there's a difference, but it actually shows that if the crack path would actually have 35 degrees, that would mean lower strength than compared to 17 degrees, because now the concrete breakout body is larger, so there's more concrete that takes the tensile stresses. So as I mentioned in the conclusions, I think that more work has to be done in relation to how well we know the orientation of these cracks, but of course, due to mechanics of materials, these laminates should be oriented perpendicular to the crack angle, so they would take the tensile stresses completely without any shear contributions. So maybe if you consider, or if you suppose, a crack angle that ranges from 35 degrees to 17 degrees, that would be an approximate answer.
Thank you, Kevin. I think it really depends on the type of loading, as you're saying, and the mechanics of materials. But you're giving an
yes.
adequate range of how to at least start considering that the problem and where to place the fibers adequate. So I think that covers the question. Sorry,
Yes.
go ahead.
That also depends on the distance between the anchor and the edge of the concrete, because we found that as you were farther from the concrete edge, the angle of the cracks were actually lower than if the anchor was placed near the concrete edge. So there are many parameters that have some incidence on that behavior.
Makes sense. Yeah, the boundary effects do change.
There's two more comments.
I don't see any other questions. Yeah, please go ahead.
Two comments, though. One is from Peter R. Abraham. He's asking, Kevin, if you could provide your email to him. You can do that
Yes,
privately through the chat box if you like, or depends on how you want to answer it. You would tell him right now, or?
Yes, I will type it.
You'll type it, okay. And then the last comment was from Vivo Y67. Thanks for the presentation, ACI Columbia. So well done. Thank you for participating in 24 hours of concrete knowledge.
Thank you, Bernie. Thank you, everyone.
And with that,
I mean, we're always happy to participate. The ACI Colombia chapter always likes to be part of this event and to share our knowledge and to be part of this great community that is ACI. And I guess they will pass the baton to the dear friends from Guatemala. Probably my friend Plinio Herrera is around there waiting for the baton. So thank you again, Bernie, for preparing and organizing this, and ACI for this event that lets us be a part of a greater community and expand the knowledge. So
yes,
thank you again.
Thank you for participating. And from our IT staff here, they said your quality of videos and the sound and everything has much improved, because in the past we've had problems. This year, near perfect. So thank you.